In this presentation, I am going to explain braking of DC motors. What are the different braking methods of DC motors? Braking of DC motors. During braking, motor is made to work as generator, developing a negative torque which opposes the rotation. There are three types of braking of motors. The first method is called regenerative braking. In that one, generated energy is supplied to the source. It is fed back to the source. That is regenerative braking. Second type is called dynamic braking, or that's also called rheostatic braking. In that one, the generated energy is wasted in a resistor. The third method is called plugging, or that's also called reverse voltage braking, assisting the back EMF in forcing the armature current in the reverse direction and produces a reverse torque. There are three methods: one regenerative braking, second dynamic braking, third plugging. That will be explaining in the other slides. Now let us see regenerative braking. Now considering a separately excited DC motor in which the applied voltage equal to VA, armature voltage equal to VA, and the back EMF equal to E, and armature current equal to IA. The basic relation IA equal to VA minus E divided by RA. And the torque produced is given by T equal to a constant K into IA. Now, this is for a separately excited motor. And for reversing the torque, what we have to do is, we have to reverse the current. If you reverse the armature current, you can make torque reverse. To make I polarity of I negative, what we have to do is that the back EM, this E should be more than VA. When we are making the back EMF E is more than the supply voltage VA, then IA will be negative. That will be producing a negative torque. For braking action, regenerative torque is to be produced. Negative torque can be produced by flowing a reverse current through the armature. Therefore, you have to make the armature current negative. To produce a negative current, E should be greater than armature voltage VA. For sources of fixed voltage, regenerative braking is possible only for the speed higher than the rated speed, higher than the base speed. Only if you run the speed more than its rated value, then only you will be getting the back EMF more than the armature voltage. But if you are using a variable voltage source, in that case, regenerative braking is possible below the rated speed. Even below the rated speed, you can bring the motor into regenerative braking mode if you have a variable DC source. Now, for you are in whatever case that to break the motor in regenerative mode, you have to make the back EMF more than the armature voltage. Then only the current polarity reverses. Continuing regenerative braking, one thing is that in series motor, as the speed increases, armature current and hence the flux decreases. Both armature current and flux decreases as speed of a series motor increases. Or as you know that one, NV is proportional to E divided by phi, or NV is directly proportional to the back EMF and inversely proportional to the flux. Therefore, as speed increases, the flux and armature current reduces. That is IA equal to VA minus C divided by RA. Therefore, as here E increases, IA reduces, and the flux also reduces. Therefore, the induced EMF cannot be greater than the applied voltage in the case of a series motor, and hence the current is not reversed. That current cannot be reversed. The IA cannot be a negative value in the case of a series motor. That is why, hence, regenerative braking is not possible in the case of series motor. Therefore, this is the equation relating IA, VA, E and RA. RA is the armature resistance plus the field resistance, and in which you cannot bring the armature current negative, since you cannot bring the back EMF more than applied voltage VA. That is why regenerative braking is not possible in the case of series motor. Coming to the regenerative braking of a separately excited DC motor, and that is done by a class B chopper. Therefore, here this is the circuit diagram. It is the DC voltage applied, and here of course to make voltage steep, there's a capacitor is connected, and the switch is connected across the armature, and a diode which is connected in the reverse direction. This is called class B type of chopper. In this case, when the motor is turned on here, what happens is that here this the generator, this is working, the motor is running, that is working as generator, that will be circulating a current through this path, and the energy will be stored in the inductor. Now when the when the switch is off here, that voltage forward bias is this diode, and that will be driving a current towards the source, or that is the energies will be flowing from the motor into the source. That is what we call as regenerative braking. Therefore, these are the voltages that is coming across the armature. When switch is on, you will be getting a zero voltage. When switch is off, you will be getting what is the DC source voltage VA, and the corresponding currents also shown here. That is during the that is a regenerative braking operation. It's called class B chopper. Now, during the on period, the switch armature voltage, the switch will be, during the on period of the switch, armature voltage equals 0, and armature current increases from IA1 to IA2. And DC machine works as a generator, and a part of this energy is stored in the armature inductance, and the remainder is dissipated in the armature resistance. And when the switch is turned off, what happens is that the armature current flows through the diode D and the source V, and the armature current, that is the current flows through this one, and that is why armature current will be reducing from IA2 to IA1. The armature current decreases from IA2 to IA1. The stored energy in the inductance and the energy supplied by the machine is fed back to the source. That is the energy stored in this one inductor and the generator, that will be fed back into the source V. This is the process of regeneration. We are driving back the energy produced here into the source. That's called the regenerative braking operation. Continuing the regenerative braking class B chopper operation here. It's a separately excited motor that is represented by armature resistance RA, LA, and back EMF. This is the motor, and this is the switch that is coming across that one, and this is the diode that is allowing the current from the motor into the source. And the duty ratio is given by here. The duty ratio is given by, during this period you are applying a voltage across the armature. That is why T minus T on divided by T. That is the duty ratio of this one. Or the average voltage that is coming across the armature is given by 1 by T integral T on to T integral V dt, or delta V, where delta is defined as T minus T on divided by T. Therefore, armature current is given by, that is the current always in this, during this operation, armature current is flowing in the reverse direction, that is in this direction, and that armature current is given by the back EMF E minus this voltage that is coming across that one, delta V divided by RA. Now, because E is more than delta V, and IA has a reverse, so a reverse torque is produced. In this armature, since the current is reverse direction, that will be producing a reverse torque, or that is called the braking torque is being produced. And the corresponding speed equation omega m is given by delta V by K minus RA divided by K square into T. Therefore, the speed torque characteristic is, that is working in the second quadrant, that is torque is negative and the speed is positive, that is working in a second quadrant. And regenerative braking has delta changes, because the parameter that you are changing is the duty ratio of this switch. As delta changes, it is operating at the different points, or this is the for different delta values, this is the torque versus the speed characteristics of a class B type of chopper that is operating in a regenerative mode. Next method is called dynamic braking. In dynamic braking, in this braking method, armature terminals are disconnected from the supply and they are connected to a braking resistance. At a braking resistance is connected to a braking resistance RB. that is disconnected from the supply, and breaking resistance is RB is connected. When it is disconnected from the supply, with field supply remains on, since the field supply remains on, the flux will be there, the motor is rotating, therefore a voltage will be inducing in this motor, and since that voltage will be driving a current in the reverse direction, armature current will be in the reverse direction, that will be dissipating in the resistor RB. When it is disconnected from the supply, with a field supply remaining on, the DC machine will work as a generator and converts the kinetic energy stored in its and in its moving part to the electrical energy, and that will be dissipated in the resistor RB. And the electrical energy is dissipated as heat in the braking resistance RB and the armature resistance RB. In the RB as well as RA, this energy is being dissipated. Now this is showing the characteristics of that one. This is it working in a forward motoring action, and at this point you are breaking that, disconnecting that one, and you are applying a resistance RB across that one. Therefore, that is changing to this operating point from the second quadrant, and this the braking operation that is finally braking, and that is finally coming to the origin. Therefore, this is the braking action and this is the motoring action. Now, this will be showing for different RB. You can change the RB value. If you are changing the RB, the rate at which it is reducing the speed, that will be different. That is, if RB is, if you are more, if it is RB is getting reduced, more current comes and it will be dissipating. For different RBs, this is the slope of the reduction of the speed. That is finally that is coming to the origin, that is to zero speed. Therefore, this is what we call it as dynamic braking. Continuing dynamic braking, and as I told you, the armature, the source is disconnected from the armature, and that armature is connected across a resistor RB. And now the current IA is given by minus C divided by RA plus RB, and for good rate of reduction, RB is decreased in steps so that the average armature current and hence the braking torque remains constant. That is, you can change the RB slowly, thereby it's a variable resistance RB, can change the RB, can reduce the RB so that the speed can be changed slowly and braking, so that the braking torque remains constant. In the case of series motor here, same thing can be used for the series motor. Now the series motor, the winding is in series. Now again the supply is disconnected and you are connecting a resistor RB across this one. And in series motor, if a series motor is connected across a resistor without any change in configuration, then it does not produce a braking torque. It does not produce a braking torque because what happens is that armature current direction, since armature current direction is changed, IA is changed. At the same time, the current through the field is also changed. Therefore, flux direction also changed. Therefore, torque is proportional to phi into IA. The polarity of the armature current and the polarity of the flux both negative. So that if you multiply that one, torque will become positive. Therefore, in that case, if you change like this one, it won't produce a braking torque. Therefore, as motor current tends to reverses, it tries to produce a negative flux, and the torque polarity does not change. Therefore, torque polarity does not change. Therefore, the dynamic torquing is achieved by reversing the field connection before the motor is connected to the braking resistance. Therefore, in a series motor, you have to reverse the direction through the field current, then only it will be producing the reverse. That is, we have to, the polarity of the current and polarity of the flux produced should be the reverse, the opposite. So then only it will be producing a reverse torque. That is required in the case of a series motor using the dynamic braking. In this case, you can see that one in a series motor, this is the forward motoring action, and this is the braking of, that is the second quadrant operation. This is the braking action. From the motoring action comes to the braking action, that's finally comes to the origin. Continuing the dynamic braking of a separately excited motor by using a chopper. In this case, you can change the duty ratio of the chopper, and thereby you can change the RB value. Therefore, this is a separately excited motor represented by RA, LA, and back EMF. And across that one, you are connecting a switch, transistor switch is the and across that one the resistance RB is connected. By therefore during the interval 0 to T on, that is during the interval 0 to T on, what happens is that switch is on. When switch is on here, the current will be increasing from IA1 to IA2. That during the on period, the current increases from IA1 to IA2. And during the time T on to T, this switch is off. During that period, what happens is that the current will be decaying from IA2 to IA1. At that time, the energy stored in this inductor is gone through this RB, and that will be dissipated in the resistor RB. Therefore, during the interval T on to T, IA decreases from IA2 to IA1. A part of the generated energy is stored in the inductance during the on period, and the rest is dissipated in RA and the transistor T. That is what is happening during the on period, and during off period that will be dissipated in the resistor RB. The energies generated and stored in the inductance are dissipated in breaking resistor RB, that is dissipated in the resistor RB. Transistor TR controls the magnitude of the energy dissipated in RA, and therefore that controls the effective value of, that is the effective value of the RB, that is RB effective value is controlled by controlling the on and off period, or duty ratio of the switch will be controlling the average value of the RB, and by controlling the average value of the RB, you can control the power dissipated in the RB. Thereby, you can vary the braking operation, the speed at which it is braking, that can be controlled. That is the principle of dynamic braking using chopper. Continuing dynamic braking of separately excited motor by chopper control. If IA is assumed to be rippleless, the DC energy consumed by this RB, that is EN, that is by RB during the cycle of the chopper operation, that is energy consumed by this resistance EN is given by I squared, that is IA squared RA into T minus T on. That is during that period the energy is being dissipated. During this period that is energy dissipated in the resistance. Therefore during T minus T on. The average power consumed by RB, that is given by the energy divided by total time period T. Therefore it is equal to En divided by T, which is equal to Ia squared RB into T minus T on divided by T. So that's equal to Ia squared RA into 1 minus T on by T, that's called the duty ratio, 1 minus delta. Therefore here the effective value of RB, that is RBE, is given by, which is equal to the power consumed by RB, that divided by the corresponding power divided by Ia square. That will be giving, it is equal to RB into 1 minus delta. RB into 1 minus delta, or that is the effective value of this RB. RBE equal to RB into 1 minus delta, where delta we are in this one you are calculating is equal to T on divided by capital T. The effective value of the braking resistors can be changed steplessly from 0 to RB as delta is controlled from 1 to 2. If you controlling this value of the delta from 1 to 0 here, the value can be changed from 0 to RB. This value of this RBE can be changed from 0 to RB. Like that one, that by controlling this value of the RB steplessly, you can change like this one. RB value can be changed, and this can be brought into the initial 0 value. That is, this is the way in which the using the chopper, you are varying the duty ratio of the transistor or the switch, and thereby you are varying the resistance value applied, and thereby you are varying the speed change during the braking operation. That is what we call it as dynamic braking using chopper circuit. The third method, what we call it as plugging. Plugging means that you are applying a reverse voltage across the armature. Therefore, this is the circuit with a separately excited motor with armature and source and resistance, etc. Here, a braking resistance RB is connected in series with the armature to limit the current. Here, armature to the limit current. Therefore, for plugging operation, the supply voltage of a separately excited DC motor is reversed so that the armature current is reversed and the armature, that is supply voltage, is reversed here, and then armature current is will be, now it is equal to minus V minus C divided by RA plus RB. Therefore, the current will be increasing because the supply voltage will be adding with the back EMF, so that the current will be increasing. And in order to limit that current, in order to limit that current, what happens is that we are introducing a resistance. Here actually, rather than for changing the polarity of the voltage, what we have done here is that armature polarity is now reversed. Anyway, the voltage across the armature is reversed. That is what is happening. And due to this, back EMF is adding with this voltage, current will be increasing. And to limit that current, we are adding a resistance RB in series during the plugging operation. Therefore, this is the motoring operation. And during the plugging operation, that is working in a second quadrant, and the speed is reducing to 0 value. Therefore, for plugging of this series motor, armature alone is reversed. That is, alone armature is reversed in the case of a series motor. Here, armature alone. This is a case of a series motor, and this is the case of a shunt motor. In shunt motor, here the polarity, now the here voltage is there. It normally will be connecting A1 here and A2 here, and the voltage polarity, now it is reverse here. The voltage polarity minus here and plus here, and the reverse voltage is applied, and that will be producing a current magnitude which is equal to a reverse. It will be driving a current in the reverse direction, and it will be producing a reverse torque. This is the first quadrant operation. This is the second quadrant operation, the breaking up. This is for a shunt motor plugging operation, and this is for a series motor plugging operation. Now let us see a problem on this one. A 230 volt, 960 RPM and 200 ampere separately excited DC motor has an armature resistance of 0.02 ohm. Motor is operated in dynamic braking with chopper control with a braking resistance of 2 ohms. First one, calculate duty ratio of the chopper for a motor speed of 600 RPM and the braking torque of twice the rated value. Second, what will be the motor speed for a duty ratio 0.6 and motor torque equal to twice its rated torque. Now, at rated operation, back EMF can be calculated as 230 minus 200 into 0.02, that is V minus IARA, that is 226 volt is the rated back EMF. That is the back EMF corresponding to the speed 960 RPM. Now at 600 RPM, corresponding back EMF can be calculated as E equal to this 226 divided by 900 into 600, which is equal to 141.25 volt. Now during the dynamic braking, what happens is that during the dynamic braking, E equal to IARA plus IA into RBE, equivalent value of this resistance, IARA plus, because the current is in this direction, that is equal to IARA, the drop in the armature resistance, plus the drop in this external RBE, equivalent value of the RBE, or where RBE equal to 1 minus delta times RB. For RBE equal to 1 minus delta RBE, or that is equal to, that can be equal to, from this equation can be written as E by IA minus RA, E by IA minus RA, that is equal to equivalent value of the resistance RBE, or that is equal to, or RBE equal to 1 minus times RB, or 1 minus delta times into RB, that is equal to, substituting for E and corresponding current is twice the current. The first problem, the current is braking torque and twice the rated value. Therefore, that is why it is equal to 2 times 200 minus RA, 0.02 ohms. That will be getting the corresponding duty ratio is given as 0.83. The corresponding answer is 0.83. Second part of the question, duty ratio is given as 0.6. Corresponding to duty ratio 0.6, as you know that one, the basic back EMF equal to IA into RA plus 1 minus delta times RP. And back EMF is equal to, 2 times, that is the current, that is 2 times the rated current, that is the 2 times 200 into 1 minus delta is given as 0.6, that into 2, that is RA equal to 0.02 ohms. Therefore, and RB equal to 2, that's into 2 plus 0.02 ohms. And you'll be getting the back EMF is equal to 328 volt. Now the corresponding speed is the question. The speed is given by 960 divided by 226 into this back EMF 328. And the answer is 1393.3 RPM. That is corresponding to the delta 0.6 duty ratio. That will be running at 1393.3 RPM.